For the morning session, I'm super excited that just happened to serendipitously have two talks on learning mixtures. Fanny is a new professor at ETH Zurich, and she's already like a leader in the field of statistical learning theory. So happy to have you here. Thanks for here to talk.
And Matus for the invitation. Disclaimer, I'm still recovering from a bad cold, so if I'm a bit slow, maybe that's useful. Yeah, hope that's okay. And also, so this work is joined with, or is led by Daniel, who is over there, and Raris, and Stefan, and a bunch of others, like especially David here, who's a colleague at Zurich. I'm going to talk about a problem which is related to topics that some of the people here are much bigger experts on. But I still, and I wasn't aware of when I started thinking about some other motivated question that then somehow I stumbled upon these topics. So even though it's a bit more removed from my main lines of work, on a technical level, I was quite intrigued by many concepts that appeared while thinking about the problem. And I also think that could be interesting for both the ones that are technically familiar and those from the broader ML community. Maybe I'll start with the process of how we got to the problem. This takes a little while. So my mind generally gravitates towards finding trade-offs between natural objectives we might care about in machine learning, and especially notions of robustness. So most of my robustness work so far was on robustness against perturbations or shifts during test time, or things like group fairness, where you care about small groups in your distribution rather than just the average. So on a very high level, the two objectives I'm going to discuss today can be viewed as robustness during training time versus robustness during test time. So then what do I mean by this? So I'll first show the two objectives separately. So first objective is to be robust against outliers. So the canonical example would be high-dimensional robust mean estimation under additive contamination. What that means is we sample from a distribution with a particular mean, here this dot, we call this distribution P, we have IID samples from it, and we want to recover this mean. So get an estimate that's close to this large dot over there. But instead of having just samples from this P, we also have samples, we have not just samples from the P, but also samples from some adversarial noise distribution, or just some noise distribution for which we don't know what the distribution is. Okay, and so we do not know, of course, which ones are noise, which ones are actually the correct ones. So if we just take a naive mean estimate or empirical mean estimate, this would be non-robust, so it would be skewed towards the adversarial distribution, right? It can be arbitrarily far. So what we want instead is a robust estimate. And what we could do is to say, okay, this blob over there, it looks much different than the rest. So we just ignore everything that looks very different. And then we just take the empirical mean of the rest. So we filter out these points that look very different. Okay, I have to say this problem originates back in the 1960s by Huber, Tukey, etc. A lot of people have worked on them, and others in the room. Right. So the goal here for the first objective is we want to somehow ignore the points that look very different to get a robust estimate of the mean. What's the second objective? Let's say we don't just have one mean, but we have multiple means, and each of them appear with different weights. So we sample from a mixture where each component appears with a weight Wi, or frequency Wi. Okay, now you see that a lot of points center around the two bigger clusters, and there's one small cluster over there. So the second objective is that we want to represent, we want a list of, we want to output estimates of the means such that for each of these true means, there is a good mean that represents them, or that is close to the true mean. So we also want a mean that's close to the mean of the small cluster, a small group. So we don't want something like this, right? So in this case, we would be ignoring a minority group, but we want something more like this, right? A list that represents minorities as well. Okay, so these are two objectives. We want to be robust against outliers, and we want to also be able to have a good group performance. The second objective is to have good small group performance. So now what if we want to have both at the same time? So what would be the problem? We're still sampling from a mixture, but now we not only have ID samples from the mixture, but we also have samples from the adversarial, some adversarial distribution, some additive contamination. Okay, so in this case, if we just outputted the number of components that we expect, which is 3, then there's very likely going to be a problem that we miss one of those clusters, and probably we will likely miss one of the two small components, since we can't distinguish them. And if we want to be robust, right, then we need to ignore some outliers. So we could just ignore the small group over there, not knowing that these are actually true points and the other ones are outliers, right? So if we just use some robust algorithm off the shelf, then this might happen. So it's robust for some I, it's ignoring some points. And so for the large groups, it's doing well, but for the small group, it's ignoring it.
Are you assuming that the can only do additive contamination?
Additive, yes.
So no removal?
Yes, no removal for this mixture problem, yes.
And that's inherent? Like you can't handle removal because of these small groups, or?
Yes, exactly. So if you were able to, then.
And the number of components needs to be known.
Yeah, we'll get to this. So this is like if you were to output, you know the number of components, and you would output the same, but not for our later algorithm or learning problem. This is just what do we try to achieve? So just in summary, in this joint problem, we want to both be robust against outliers, like the red points. We don't want them to shift the mean estimates too much. So we want to filter out points that look different. At the same time, we want to preserve minority groups, and which means we want to keep points that look different. Okay, so that obviously leads to some kind of trade-off or battle of these two objectives. So points that look different include both outliers and minority groups. So the algorithm doesn't know which ones to keep and which ones to filter out. So I was interested in trying to formalize this trade-off. I didn't really know what that meant when I started. But maybe one refinement of this problem, of this question, is, can I quantify the cost of preserving small groups under adversarial corruptions? Right? Adversarial corruptions that can be larger even than the weight of the small group. So that's maybe one way to kind of try to formalize this question in the first step. Okay, so then maybe let's look at a more formal introduction of this problem with a bit of notation. So we're going to look at a Gaussian mixture with additive contamination. The Gaussian part is cleaner to present, but the general framework also allows for central sub-Gaussian moments, for which we can get guarantees. But the whole presentation will just focus on Gaussians for simplicity. Okay, so we assume we have k components. That's our number of components, true signal. Wi is the weight of each component. Epsilon q would be all the adversarial points come from there, and q is arbitrary. Adversarial epsilon is going to be our corruption proportion, which means that the sum of Wi plus epsilon sum to 1. This is just a bit of notation. We assume spherical Gaussians. And we know that. So all the Gaussians have identity covariance. And the means are mu I. Okay, so what does it mean to allow adversarial corruptions? You saw some examples already, but really the adversary can place these points arbitrarily, right? So they can place them uniformly. It can be trying to derail the estimate of particular clusters, or just one cluster. or multiple, or just add fake clusters, like multiple ways to add Q. And the goal is, for the worst case adversary that you can think of, given some IID samples from this PX, recover all the mu i's, so the means, for which the component weight is larger than some user set W low. The W low is the lower bound of the group sizes of the group components that we want to recover. And at the same time, the proportion of noise is larger than this W low, which means it can overwhelm small groups. Now, just for the rest of the talk, you can just consider W low is equal to the minimum of all Wi's, just for simplicity. But you could theoretically just you can think of it as the algorithm is getting a W low, which is what the user really cares about, group sizes that user cares about, and then the rest just goes into the adversarial part. Okay. Now, under this slightly more formal definition of the problem, how can we get closer to this goal of formalizing the question that I had before, this trade-off? So first of all, we need to think about a paradigm under which we can actually recover the means under corruptions, where summaries a question will come up, right? Like, what is the number of components you know in advance? And then second question would be closer to the trade-off question is, what's the cost of choosing a small W low, right? What's the cost of caring about small groups of size W low roughly that are smaller than the corruption proportion?
So for the groups that are like smaller than W low, does the algorithm like implicitly assume that they're outliers, or is it just something different?
Basically, yeah, you can think of them as being part of the outlier.
Okay.
So basically, you don't care about estimating the mean, so you can treat them as outliers.
Okay.
Okay, so what's the problem here? If we want to recover those means, outliers are indistinguishable from the true minority. So filtering with a fixed size k, if you knew the size k before, number of components, wouldn't work. As I said before, if you knew k was 3, you would possibly just get 3 and ignore the small component over there. However, okay, so this was the wrong animation. So however, what comes to the rescue is the paradigm called list-decodable learning, where you can output more candidates for the means than the number of true means, right? So even if you knew k equals 3, you just say, okay, I allow you to output me more than k equal to 3, any number you want. This is what essentially list-decodable learning, the mindset is, right? So there might be very bad adversarial noises. I cannot identify which ones are the ones I care about, which ones are not. So kind of I just output a list of possible candidates. So this framework was actually coined in a paper 1957 in the info theory community for error correcting codes by Peter Elias. And it's used for many other problems, not just for mean estimation or mixture learning, also for linear regression, clustering, and many more, where people here have worked on those problems. Okay, so this decodable learning would allow us to output 4, which captures both the true means, but also mean of a fake cluster you don't care about. Okay, so what is the formal definition of this paradigm? Of the learning problem is we know W low, okay, we don't know the rest. That's the only thing we're given. The algorithm is given W low and some data points from PX. And then the goal is to output a list with list sizes larger than K, usually larger than K. If there's no noise, it can also be K, such that, of course, so if you look at possible lists that can output, you can also think of just covering the entire space without seeing the data, and then probably you're going to be close to the mean. And so we want the list size that's reasonable. And okay, maybe here we want a small list size overhead. And with that small list size overhead, we want to be able to have small estimation error for all components that are reasonably sized, so that we care about. Okay, so for any component I, there's some mu hat in this list that is close to mu I. That's the list-decodable mixture learning problem. Difference to problems before, or robust mixture learning, for example, is that here we allow epsilon to be larger than W low. So this has not been studied before. And that was interesting. So this is kind of a problem we came up together then with David's lab, because I was interested in this trade-off. I was thinking, okay, how do you formalize it? But if you don't go into this list-decodable learning paradigm, you can't even start to formalize this trade-off. Yeah.
Partition of the data or no?
Yeah, you'll see that. Yes, basically you can think of that. So if they're separated, then you'll get a mu hats that will cover the separated groups of clusters.
But the goal doesn't require that.
I mean, the goal doesn't require. The goal is just that the true means should be to be covered.
Sorry, is the value of W
You can think of like W, for example, is like 1 over K or something, or normalized, but this is arbitrary, right? So we allow arbitrary choices of WI. Of course, they should sum up to, yeah, and we assume that the sum of WI plus epsilon is 1, so in that sense. Okay, so yeah, interestingly, this has not been studied before. So starting from a very different question, and we ended up finding a question that also David's group found interesting. They found like technically it's unclear how well we can do for this problem. So then we started working, or Daniel and Rara started working on, can we find an algorithm that achieves a good list size and estimation error, and what are the limits, and are we optimal? Okay, so what is the goal now? So that was the original question that was kind of vague. Now the question is a bit more refined, which is quantify how much the estimation error on large groups, if we care about estimation error in small groups, increases, and the list size increases with W low, right? So the smaller the groups that we care about, we expect probably there's a cost for the error in the list size. And we care about polytime algorithms. Right? So Adam only wants to listen to talks where the algorithms actually can be implemented.
I mean,
Yeah, I'm just yeah. Okay, now I agree. So this is the question now. What can be achieved and how optimal is it? So I'll talk about the algorithm only in the end. Let's see, hopefully get there. So what is a naive approach, first of all, that already exists in the literature, not for this problem, but can be used? That's just using list-decodable mean estimation off the shelf. So you can think of, if I care about a particular component J, right, one of those components, one of those Gaussians, I can just rewrite this, this mixture by just isolating Wj times the Gaussian around mu j. And then the rest I can write separately. Or rather, I could make the problem harder and say, okay, I isolate this, and the rest I just treat as outliers. Right? So if I can solve this problem, like if I can recover mu j from samples here, then I can also recover mu j for the other problem. But so this is a bit of a harder problem because you allow Q tilde to be arbitrarily adversarial, whereas in the other one, the other clusters are not, strictly speaking, adversarial points. Right? So we do care about them. So to some extent, you can think of this problem being a bit harder. But if we can recover mu j here, we can recover mu j there. So that's kind of the idea. So you could use a list-decodable mean estimation algorithm off the shelf to solve that problem. Like for each component, you can be sure with high probability to find a list that has mu hat that's close to mu j for every one of them. If you make sure that you choose in your list-decodable algorithm, you need to say list-decodable mean estimation, you have to say what's the expected proportion of the inlier component. Not expected, but what do you think is the, if you know it, then you input the proportion of the inlier component. In our case, that would be W low. And if W low is small enough, then you can recover all of the WIs that are bigger than W low, just by using LDME with this W low. Okay, so what happens if we do that? So here I'm gonna show the guarantees for different algorithms in this table. Hopefully, so it's easier to compare, and hopefully it's clear what the guarantee means. So basically here we'll have for each column, or for the first 3 columns, we'll have different algorithms. And what the column will mean is, so the algorithm, which is on the first row, output the list size, second row, such that the estimation error for a component I, which is the mu hat minus, which is mu I minus some mu hat in the list, is upper bounded by whatever is in the third row with high probability. Okay, this is how to read the table. So let's read the first column, which is just using LDME, which I just presented. We would be able to get guarantees. And the guarantees would be, we output a list of size order 1 over W low with an estimation error square root log 1 over W low. So that's the typical, if you know these, like if you're aware, if you know this literature of uniform weights, then W low would just be 1 over K, and then you would get the guarantees that you're familiar with. Okay. Yeah, so this is for polynomial sample. So basically all of this work is sample size polynomial and everything, D and 1 over W low and things like that. They don't really look at the fine-grained sample complexity. Well, okay, so if you look at this, the problem of this guarantee is the estimation error is square root log 1 over W low for all of the components. Meaning, even if you're much larger than W low, this algorithm is going to give you a bad error, which is maybe unnecessary because you're actually large. Right? So this is a big components suffer the same error. So this is what the problem with just using LDME is. Okay, so W low is too small of an estimate for weights of big clusters. So if you just output W low, it's going to be very conservative. The other challenge is that you might not want to view the other inlier clusters all as outliers, right? Because they actually, they're useful. You actually also care about them, and maybe there's a way to identify them as good outliers. Yeah.
W low is the weight of the smallest cluster, so you don't care about that when you. It's just all WI.
Yes. So for the smallest cluster, this is a good error, but for the bigger clusters, it's not the optimal error.
Or is it greater than equal to W?
Oh, what did I say? Okay. Yeah. Equal. Yes. Yeah.
So just one question there. Do you make an assumption on the separation?
Yeah. It'll come. So this doesn't require. The next one also doesn't require. And later, yes. Okay. So the second, so we wanted to tackle these challenges. So in 2 steps. Okay, basically our algorithm consists of 2 stages. One stage tackles one of the problems, and the other stage tackles the other one. So the first step is if we just take one of the stages of the algorithm, the inner stage, then we're able to get this guarantee, which is that for arbitrary separated clusters, so it can be arbitrary close or non-separated, we can get a guarantee that depends on the cluster, at least on the cluster size. Square root log 1 over WI, just by basically doing some grid search over the weights of the clusters for each of them. But that's still not good enough in the sense that we are still kind of treating all the outliers, all the inlier clusters that are not the component I, we're treating them as all as outliers. So we kind of feel like maybe we can still do better, and that's if there's structure in the sense of separation, then we can do better. That's exactly the idea. So if we have well-separated Gaussians in the inlier distribution, then we can get much better both list size and estimation error. List size is k, which is the number of components that you cannot reduce, plus of order epsilon over W low. This is also something you cannot reduce, that I will describe in the next slide, or one of the next slides. And then the error, you can think of it as basically as if as if somehow magically your algorithm knows knows that basically over here. If you care about, which one do I care about? If I care about this one, that I basically ignore the presence of these, right? I just have one component and the outliers. So I don't treat the other true inliers as outliers. Somehow, if I can magically do this, which I can do if I have separation, then I can get this guarantee, which is the best you can get, just like a mean estimation problem, but without any of the other components. So epsilon plus wi is just a normalization, right? So wj over epsilon plus wj is just the proportion of the true inliers. So that's again from the mean estimation point of view, it's 1 over the weight of the true inlier component. Yeah.
Means, or like if you have like two clusters that are super close together and like you have like one mean of one of them, can you reuse it, or would you need to like put it out twice in the list?
I reuse mean prune it.
Like, let's say your list consists of like 5 and 1, and you have like one cluster at 4.9 and one at 5.1. Like, is this a good solution, or is it like a bad solution in this case?
So you're saying whether you can, whether it's a good solution. Okay, I mean, the thing of it, there is a mean that is like unnecessarily there. So the list size is unnecessarily long. So it would be it's not optimal solution.
That's yeah. But like if you have like two clusters with the same mean and you just put out the one number, would that be like an acceptable solution?
What is two clusters with the same mean? Then it's just a larger weight of the same cluster.
Yeah, more like thinking about the limiting case anyway.
Yeah, but that's the thing. So here there's the separation here, right? I mean.
Okay.
Yeah.
Take it offline maybe.
What is the order of separation?
It's square root 1 of log 1 over W. It's the standard separation that you also have for mean estimation.
Here, your Gaussian is any covariance Gaussian?
Yes. Sorry. Is
Yes.
It's identity. Yes.
It's identical.
Yeah. Sorry.
Okay. So if you I guess my question is more if it was an identity, how would the separation depend on variances and plus WIs? But don't worry.
Yeah, that's what we can take offhand. Yeah, we were thinking about the non-identity covariance case, but it's you need to estimate and yeah.
Is there any hope to, I suppose the right constant on the second term is 1 or something like that, that you should be able to get?
Oh, this one?
Yeah.
Yeah, but even for mean estimation, you kind of get 1 yeah.
But well separated.
Even there. Daniel, do you have anything to say? Is there hope to get the right constant there?
Probably. So I think yes, but it needs some work.
I don't think there's a simple separation assumption even for regular learning Gaussians that are non-identity covariance.
I mean, it depends on whether you're using method of moments or plus.
Yeah, I'm just saying, I don't think there's like there's whatever root log k is like the simple separation assumption for identity covariance.
No, but it's really if let's say it's all sigma squared ID, for instance, right? Then I need the cluster mean separate by this order sigma.
Sure.
Yeah, that's scaled with the sigma. Yeah.
The question is how dimension comes into play, right? So technically, one could imagine square root d in the dimension or order 1. So it really, I'll ask the question.
Yeah. Okay.
Sorry, you have one more question.
Yeah.
I'll give you the time back.
Okay.
This is just like a basic methods question. Do any of these algorithms resemble like doing an EM type method, but having assignments for also the outlier group as well? Like, are there any methods of that form for this? is that an approach you could use for this problem?
A good question, like for this robust thing.
I think that there are methods who try to put weight on the samples, and if something is outlier, then they put less weight and they update it.
I kind of meant like in the same way that EM estimates assignments, cluster assignments. Could you also have outlier assignments as a one additional group, right?
Yeah, that's one of the. But,
Okay, that
but
is
here we abstract out.
Okay, so maybe let's try to get to the algorithm in the last few minutes. So first of all, okay, so now we've parsed the guarantees that we have for the separated case. Compared to LDME, there are many differences, of course, the list size, but also if you think of number of corruptions, the percentage, if it's roughly similar to the percentage of the inlier, then you'll have a big gain here. 1 over W basically, log 1 over W versus something of a constant order. And so then I want to go back to the question that we started off with the trade-off, right? That's what I was curious about on a high level. Can we quantify somehow this trade-off? And so if you look at it, the estimation error really does not suffer from caring about small groups. The only thing that suffers is the list size. And that is actually not preventable. And that's what I want to show in the next slide. So basically this, okay, the constant, ideally it should be epsilon over W low, if we can achieve it, unclear, but why we at least need K plus epsilon over W low. Okay, so that's kind of trivial for Siva, but still say why, right? I mean, so just imagine your epsilon is equal to 3 times W low, or W low is the smallest cluster, let's say this one. And you have budget that is 3 times the weight of the smallest one. So what you can just do is use this budget and place 3 clusters of this weight in different places, right? And so if you do this, you basically need to output all the true components and these epsilon over W low fake clusters, because otherwise you don't know which one is fake and which one is true, so you have to cover all of them. Okay, so in this case, you would have 3 plus 3, which is epsilon over W. So this is, the total list size has to be at least that. This is something you cannot do better. But of course, the constant here, we're not super optimal. Okay. So list size is kind of clear. We definitely need this. Estimation error kind of reduces to the optimality of, reduces to low bound for the mean estimation problem, where you also cannot do better than log 1 over alpha, where alpha is the true inlier component. So this is kind of, even in the Oracle case, we have mean estimation without any of the other true inlier clusters. This is the best you can do, and so you cannot basically do much better. This is how the logic for the lower bound works. Okay, so this is the way to interpret the lower bound, because there are two metrics here. How do I interpret lower bound or optimality? Basically, a smaller list would miss one component completely. So this is definitely not what we were aiming for. And also, if you wanted smaller estimation error for all of the WIs, you would require larger or exponential list size, or even for the smallest components. If you only cared about the smallest components, you would require, if you only cared about the error for the smallest components and you wanted to be better than this, you would also require exponential list size. Okay, yeah. This is if you want, so if you restrict to polynomial sample complexity, this is what, so either, like if you want to do better, you would also need exponential sample complexity, basically. This cannot be beat if you restrict yourself to polynomial sample complex. So this is not very, I don't know, for me, it's like coming from statistical learning, it's not super satisfactory, but that's kind of the way people, and it's like an SQ lower bound style argument. Okay, now maybe to our algorithm. The framework consists of 2 stages. Basically, you use the structural assumption of separation to separate a data set into different subsets. Okay, exploiting the separation assumption, you check concentration. I mean, not just only do you utilize separation, but also concentration. So for Gaussians, that's clear, but also for the T-bounded submoments, T-bounded sub-Gaussian moments. And then we reduce, by doing this step, we reduce mixture learning to mean estimation. Right? So for each of the TIs, now you're going to run a mean estimation algorithm that already exists. You can use any of them. Of course, if you use a good one, then you get better guarantees. And that's kind of the idea of our theoretical analysis, is that we can use any black box and give you guarantees that depend on the guarantees of that black box. So we then take TI and run mean estimation. So the base learner has to be able to deal with adversarial corrupted models and ideally output small lists with a good estimation error for the mean estimation problem. Okay, so I only mentioned LDME here. You can for large clusters where epsilon is comparatively small compared to the size of the cluster, you can do even better with robust mean estimation as another possible black box learner. So you have both an LDME learner and a robust mean estimation learner that you can plug in here, and you also inherit the guarantees of that learner. Okay, so just pictorially, what is the outer stage doing? So let's say this is your setup. Inlier clusters are red and outlier samples are blue. And the goal is to split the inlier clusters into separate sets. That's the first step. You want inlier clusters to be in some TIs and not 2 in 1 TI. Okay, so that's a goal. So this is, for example, how you do it. You find regions of high concentration, isolate them, and then remove them from the original set and do this many times, right? So this is, let's say T1 is that region over there. You separate it out and remove it and do it sequentially with the next ones. Until basically it's almost empty. You do not find a concentrated region anymore, and you take everything, put everything in this last set. And so if there's a good structure, then you can basically be sure that the sets TI have points from at most 1 inlier cluster. That's important since we didn't want the inlier clusters to be viewed as outliers. 2 minutes, okay. And yeah, the rest is in T-last, which can include, some of them can also include adversarial clusters, of course, and the last one as well. Okay, inner stage, I'll just go quickly that you just do mean estimation. So now we don't know proportion alpha, which usually LDME algorithms need. So inlier weight proportion. So we have to somehow search through that. And so that's kind of what the inner stage is doing. We start with W low, which it's very small, but maybe the true cluster is larger. So we kind of search through other alphas. We do LDME for different alphas, and we get different like fine-grained and coarse-grained lists. And then we do some pruning and filtering based on concentration, and then get a small list. Okay, so this is just in 1 minute. Okay, maybe empirical performance. We actually one bachelor student implemented multi-filter algorithm and tried out how this would work in practice, but more like in experiments. And first of all, we wondered how does it change with W low? So that was the question, like what's the cost of W low? So this is kind of what we see. We're comparing LDME and ours. So the estimation error for ours doesn't really change that much. For a list size, that doesn't grow that much. Okay, and that's different for LDME, where the list size should be of the order 1 over W low, whereas ours should be K plus 1 over W low, which means it's much flatter. Yeah, don't have time. And the other one, maybe that's interesting to look at, is the comparison with heuristics as well, like K-means, DV-scan, the clustering algorithms. how well does our algorithm do? So if you look at, so k-means basically you can rule out. They're extremely bad both in terms of list size and with estimation error. So these plots are given the error of our algorithm, what is the list size for different algorithms? Okay, the other one is given a list size that we output, what is the error for different algorithms for the same list size or for the same error? And you can see that dbScan actually does really, really well. Like empirically, there's no guarantees, but for this problem, dbScan also does really well. Ours just has guarantees, but yeah, we were not like able to systematically beat them. Okay, so I'm out of time. Just in summary, what we studied is recovering small groups in the presence of large outlier proportions. It's a problem I studied before. There is no cost in the estimation error, but there is a cost in list size. We had an algorithm, proposed an algorithm that inherits guarantees from black box mean estimation learners. For Gaussian mixture, there's an optimal one. And yeah, we also showed some preliminary experiments where the performance empirically matches heuristics like dbScan, sometimes outperforms. So that's the end of the talk. Here's the paper. If you have questions, Daniel is over there with more details. Yeah, thanks a lot for listening.
Since we're still over time, let's take our questions for Fanny to the coffee break, right? So I can get Vasilis in here. But you had lots of questions during your talk, so you'll be here for the coffee break.
Yeah.
Okay, great. Thank you.